Welcome back to Finding Your Place in AI Ethics Consulting. And so now we're going to talk about bias testing. And this is going to be a little bit different than the other lectures in the sense that instead of talking very broadly about topics and skills and tasks that you might do as an AI ethics and governance consultant, I'm going to dig a little bit deeper into bias testing and just give you a sense of what it might actually entail. And I think it's one of those areas where there's going to be a lot of growth and people who could audit algorithms for bias. There's going to be a need for that. So I just wanted to touch on this a little bit deeper. So testing an AI system for ways in which it can negatively impact the interests of people, it's just one tool in a larger AI governance toolkit. However, it's a very important one, and it's an important one because it can cause real harm, and so mitigating that bias can directly affect people, and it's also one that is capturing a lot of attention in the media. And bias is one of those topics that is always talked about when people talk about algorithms, and it's one of the things that people worry about the most. So let's just dig a little bit deeper into what a bias audit is. And so let's talk about the overview, just general principles. So a bias audit tests an algorithm for bias in ethnicity, gender, disability, race, or any other feature that might lead to disparate impact. Okay, so in general, this is just one small part of a larger audit framework. And so typically, you would look for risk in the entire system, and one of the risks is going to be bias. And so a bias audit or a bias assessment is really just a sort of targeted test for the algorithmic system itself. And so there's a really great paper by the Ada Lovelace Institute, Examining the Black Box, Tools for Assessing Algorithmic Systems. And this talks a lot about testing for bias. So in general, prior to attempting a bias audit or a bias assessment, you need to first do a few things, because you can't just go in there and just start using some out-of-the-box solution or data sets and just think that you're going to get something sensible. You first have to really gather the full context of the socio-technical system around which the algorithm is in which it's embedded. And we have a very specific methodology around this, which deals with outlining the context, and we do this in a narrative fashion. We outline the context, we sort of elucidate all of the relevant inputs, we assess the decision procedure itself, i.e. the algorithm, and then we look at the actions taken from that decision procedure. And this is sort of a necessary, you have to understand all of that flow of information and the context in which it's embedded in order to even start thinking about what are the biases you need to look at. And importantly, you have to look for all stakeholders. You have to really list their potential interests and rights, or if you want to, you can focus on a more harms-based approach where you list potential harms that could happen. And then once you have that list, and you have to typically engage stakeholders to generate a sensible list, you can't just do it on your own, then you can proceed, because then you'll have a better idea what are the biases that are important. So a special note must be taken to look at power differentials and power structures, because in general, the powerless are more likely to be at risk than the powerful. This is just a general rule, and I think I might have mentioned this before in the course, but having that in your mind is really important before you even start looking at that data or the algorithm itself. And so we actually have a paper that we published. These are all BABL team members of mine, talking about algorithm audit and doing we call it an algorithm audit, but it's really more of an impact assessment, so more ethics-based audit. And right now I'm going to talk more about the technical side of the bias testing. So for the moment, I'm going to talk just about black box audits. So there are different levels of transparency for algorithms. And right now, we're just going to assume that the algorithm is a black box. We don't know anything about it except for inputs and outputs. Okay. So here's a diagram of what that looks like conceptually. You have an input, you stick it into this black box, and then you get some output. And you can think of this as simply as a function. It may not strictly be a mathematical function, but it's really an input-output. And typically, of course, there could be more than one input and more than one output. And typically, the systems that we're going to analyze affect people. And in fact, typically, part of the inputs is information about people. And so you have information about people in the real world. Then you typically have some filter. So some way of collecting that data. Maybe not all the information is put in, maybe only some subset of the information. Maybe it's a camera. The filter could be a survey or someone's interaction with a website. And so there's this filter between the people and then the inputs. And so you have to understand that filter. And in general, you typically also have to classify people into groups. And so this is either done sort of by design in the sense that the algorithm itself classifies the data, or the filter itself will classify people into particular groups. Or if you're doing the testing, you might be the one that's doing this classification because you're looking for behavior, varying behavior depending on what class or what group people belong in. And in general, if this sort of group classification, like how you group people, and the filter itself is going to introduce biases. That's just the nature of these sorts of things. And so examples of that might be non-response bias. There could be a bias where people, let's say, don't give information because they don't feel comfortable giving certain piece of information about themselves. And so you're biased towards groups that might feel more comfortable giving that information. It could be differential access to technology or services. Imagine if you're relying on a person who has a cell phone, and in particular an iPhone, let's say, in order to train an algorithm, you're going to be biased towards people who can afford an iPhone. And so you have to be aware of those biases. And that's sort of what bias testing tends to look for. But a lot of times you can get a sense, even without doing any testing, where these biases are going to creep in. So that's a sort of general overview. After you get really a clear-eyed view of what your assumptions are, what your biases are, the basic idea, the simplest idea for bias testing is that you classify inputs based on group. So it could be race, could be gender, could be ability status. And what you do is you look for systematic differences in the output. Okay, and in particular, systematic differences which are irrelevant for the task. Okay, if you're diagnosing a disease, there's a chance that what gender you are might matter, and it might be relevant for doing that diagnosis. But for the vast majority of the kinds of algorithms that we deal with, race, gender, age, those sorts of things should be irrelevant. So you look for differences, but you have to have data that has been classified. So there are two broad ways that class membership can be encoded in input data. It can either be explicit class variable or a proxy class variable. Let's talk about those two. So an explicit class variable is the case where it's actually part of the input, right? So you can imagine I have some algorithm that might be detecting the probability of being diabetic. I could have the age, race, weight, activity level of the person, and it could go on, lots of different information goes into the algorithm, and what comes out is the probability that person is diabetic. Now, in this case, on the left-hand side, those inputs are literally explicit class variables. The age, the race, you could have gender of the person. Those are explicit encodings of the class variable. So in most cases, this is not the case. So because engineers are aware of the fact that biases could happen, most of the time they go through, unless it's relevant for the task, they go through a lot of work to get rid of those class variables. Okay, and so most of the time it's not this simple. Another way you could do it, encode the classes through a proxy variable. So in this case, the inputs are only correlated with class. Okay, so zip code is a really common one. It's been found, especially in the United States, but this is true just about anywhere, that zip code and race are correlated. Yearly income might be correlated with race or gender. The image of your face, right? It's kind of hard to hide, facts about yourself from an image of a face, and so that encodes by proxy a lot of things about you. Your name, might have some cultural information that is a proxy for either race or gender, etc. And then those can get fit into an algorithm, and even though they're not explicit class variables, they don't label you per se as belonging to a particular group. They might correlate with that group, and so these are places where bias also can creep in. And then the output could be the probability of whatever the algorithm's trying to detect. So let's look at an example of bias, and one that's been talked about quite recently is the Twitter example. So on the left you have, this is an experiment where Twitter has an automatic cropping algorithm, which has since been removed. And this algorithm essentially looked for sort of the most salient parts of an image based on the sort of saliency metric. And it would locate that place in the image and then crop around that. And it turned out that through experimentation, it turns out that it is going to preferentially crop around faces of people with lighter skin. And this has been shown, in fact, to be true. And Twitter did their own research and published it, and have since worked to correct it and in the meantime, removed the algorithm. Zoom had another example where Zoom has a feature where you can replace the background. This is something a lot of us, especially in the pandemic times, are quite aware of. But it has to identify who you are or where you are in the image as a person. And this is a researcher on the right talking to his advisor, who is a person of color, and it didn't recognize him, and therefore it just replaced him with the background. And the irony is, when this researcher posted this on Twitter, he actually ran into the same problem on the left, where it cropped around his face when he posted an image which did have his advisor's face in it. And so this was double bias. This is just one example. There are many, many examples. In fact, the gender shade study is probably the most famous example of sort of that and the Compass recidivism algorithm are some of the two most famous examples of sort of a bias in an algorithm. But there are so many examples now that you can't even list them all. So let's look at this particular example and how we might approach it. In sort of our methodology, we have what we call feature metrics. So the metrics are facts about an algorithm that can be measured or assessed in some way. And so this metric in this case is bias in essentially a face detection algorithm. What are the potential harms? So in this case, the harms could be excess labor. So if a person has to adjust the image or fix something that was cropped improperly, or they have to adjust their background or change some setting in order to be seen on Zoom, that's excess labor, and that's a harm, and it's differentially applied. It's not applied equally across all groups. Feelings of frustration and exclusion, this is real harm. This is emotional distress, and people have actually talked about trauma. When you have to go through all of this work just to belong and just to get an education, let's say, that could be traumatic. So the rights and the interests that are involved could be non-discrimination, right to an education, right to a job, etc. So what's the general strategy? We might use the test. So you might test the performance of the algorithm on specific intersectional groups. what you want to do is you want to quantify the bias, and you also want to determine the source of the bias. And probably my head is in the way of some of this, so I'll post the slides so you can see the full example here. So how might you approach this? Let's just talk really generally, because there's many subtleties to this, and which is what makes it such an interesting field of research and interesting endeavor to undertake. But how might you do this? So you have to sort of split apart. You have to somehow classify people, right? And again, this is just doing this can introduce biases even in the testing. Okay, so you have to really be aware of what you're doing. But let's say we want to tell how accurate a face detection algorithm is between groups. So one group might be white women, and another might be black women. Okay, then you can maybe have white men, black men, and then you can have other groups as well. But let's just look at the two groups. So here we have 3 images. So we need to get the input data, which somehow has to be classified, right? And so you have to find images, and in this case, it's just visual. So I was doing the classification, and I looked, and I got 3 images of 3 white women. They're different ages, they're different orientations, and you run a face detection algorithm on it. Now in this case, I didn't actually run an algorithm, I just drew a box over it just for illustration purpose. And then I say, okay, let's say I only have these 3 images. I want to somehow test for bias. So what I might do is I might find 3 other images, this time of black women. And I want to say, how well does the algorithm work on these 3 images? And so let's say I do it, and then I see that the middle one, which is I've outlined in red, let's say it fails to detect her face. Okay, and so now I have 2 images or 2 different intersectional groups, and I have 3 images each. And in this first case, it's detected all of them, and in the second case, it didn't detect one. Okay, and so this is all I have for data, and it probably doesn't take much understanding of statistics to realize that you can't actually infer anything from this experiment. There are some indications that there might be bias in this algorithm, but you need a lot more data to do it. Now, the reason is there are so many other factors in these images. These images are different, and I've taken care to try to match them. So if you look at the left, there's a woman with glasses who's looking at a phone. There's a woman who's looking directly at the camera. And then there's a younger woman who has a profile image. And you can see that I've tried to mimic that here. So to the extent possible, one of the hardest things to do when you're trying to detect bias is you have to hold as many things as possible constant and only vary the things which are relevant to the class. And in this case, it's just proxy relevant in the sense that we're just using an image. And this is a very difficult thing. And what you typically need to do is use a huge amount of data, because slight variations in these images could be the cause of, let's say, a failed detection, and might have nothing to do with race or gender. So in order to get statistical significance, you typically have to use lots of data. And understanding how much data you need and how significant those observations are is most of the battle for doing these sorts of testing. You have to be aware of your own biases. You have to be careful that you're labeling data in the right way. And just getting the data is difficult. And so there are a lot of challenges for doing this testing. And this is just a sample of what it might take. So statistics from large numbers can help reveal trends that are really hidden by isolated examples. And that's part of the battle of doing this, is that there actually is a lack of data sets that are sufficient size and a sufficient quality for actually doing this testing in a lot of cases. So let's now talk in general. Let's sort of sum this up here. AI governance, what can you do about this? So, you've now listened to sort of a whole list of the types of things that you might do as an AI ethics and governance consulting. There are many, many more that I didn't cover. I just talked about my own experience and the things that I've seen. But it's a fast growing field. There's so much to do, and it's so important that people do it. And we really need new people and unique perspectives to sort of fight these potential negative effects, because the fact is the world is using AI and it's just going to get worse. And so we need more people thinking about AI governance. So what are the ways you can do that? You can become an AI engineer and bring your own voice to the table. So you can get into the actual engineering and bring your perspective to that, to the development of these technologies. You might just call out biases when you see it, right? And this is a really important advocacy. You know, hold companies responsible for their products. You can advocate for regulation around automated decision making. So you might try to push regulators to do more about it, and to pass legislation on this. You might just want to increase awareness about the use and retention of personal data, or raise awareness in general about AI. One thing you could do is become an AI governance consultant or an algorithm auditor, and that's something that I focused on, and I think it's a worthwhile thing to pursue. So next, we're going to try to do a self-assessment, and the goal is to figure out where you are now and where you want to be and how you're going to get there.